do. I figured we could focus mostly on integrals because I think that's what most people have most problems with. And we'll start though we'll go in order with the syllabus. So we'll start with linear algebra and then do differential calculus and then integrals. And I muted everyone just because since it's a lot of people, I didn't want there to be background noise, but feel free to unmute yourself at any time if you want to ask anything. And I'm not sure if there is a chat, but just don't use the chat because I won't be able to see it as I'm screen sharing. And also afterwards, I'm gonna send the recording and the solutions. So in case you miss anything, you can also see it later, but you can just stop me at any time as well. Okay, so I'm gonna start screen sharing. So the first exercise that I picked was one from, should be last year's partial, the second shift, I think. And I wouldn't worry much about the definitions and theorems that they asked in the last partial, because usually they don't ask the same exact things from year to year, at least when it comes to definitions and theorems. So I would just do part C here. So the questions on eigenvalues and eigenvectors are usually pretty straightforward. This one is a little bit more difficult in the sense that they give you different information than they usually do. So I'm looking here at part C. So we have a symmetric matrix, as we always do with eigenvalues and eigenvectors. This notation just means is a 2 by 2, so they might also call it a matrix of order 2. So since it's symmetric, then if usually we would call a matrix, or we would call the numbers in a matrix A, B, C, D. In this case, when it's symmetric, we can say that the numbers that are reflected across the main diagonal are going to be the same. So B and C are the same. So you just want to immediately maybe call them both B or call them both C, just to make it simpler. And we know that the trace is equal to 0. And then we have an eigenvector with the corresponding eigenvalue. So two things to keep in mind with eigenvalues and eigenvectors is that in the more theoretical questions, you often need to use one or both of the main conditions that eigenvectors and eigenvalues satisfy. So the first one is just the definition of eigenvectors and eigenvalues, which I think everyone is probably familiar with, just that if you multiply a matrix by the x vector, you have to get a multiple of the x vector, where that multiple is the eigenvalue. And with eigenvectors, it is assumed that the vector is not the null vector. So the null vector is an obvious solution to the equation, and it's not considered an eigenvector, even though it is a solution. And if we rewrite this, if we move everything over, this will become ax minus lambda x equal to the null vector. And then if you rewrite this further, this you can write as lambda times I. I'm just going through it a bit quickly because this is something that comes up in at least one proof, so I think most people are familiar with it. Anyway, the point is that you end up getting this result. So these two statements are perfectly equivalent, but if they do ask you for the definition, this would be the more standard writing of it. But in practice, this is going to be a little bit easier to use. So they are equivalent, but you just want to be familiar with both. So this can be relevant when they give you some information regarding the eigenvectors, like they do here, that they give you one of the eigenvectors. So we know that this is a solution of the system, whether you look at this or this, it doesn't matter, but I think this is going to be a little bit nicer to work with. And the other thing that we have is that, of course, to find the eigenvalues, the rule is that the determinant of this must be equal to 0. So this comes up pretty much all the time. And just so you know, in case you had written this in a different way by subtracting this to the right side, you would have gotten determinant of lambda I minus a equal to 0, and that's perfectly fine too. So it's just not the way we usually write it, but they're equivalent statements. So I've noticed that in a lot of fantasy proofs, I don't think they are very likely to ask fantasy proofs, but it's still useful to keep in mind that for these theoretical questions regarding eigenvectors, a lot of times you're going to be working with these equations. So one of these two, and then the classic one, which just says that the determinant of this matrix is equal to 0. So this we can use to find the eigenvalues. Notice how it has nothing to do with the eigenvectors, so it's not useful when they gave you information regarding the eigenvectors. It's only useful for the eigenvalues. And this instead takes both into account. So they're kind of useful for different reasons. And also, when you're looking for the eigenvalues, we have the shortcut to avoid having to go through this procedure. So this is a shortcut to find the lambdas. And that's that the trace, which is just a sum of the numbers in the main diagonal, is equal to the sum of the lambdas. So generally it's equal to lambda 1 plus lambda 2, and so on. And the number of the lambdas is the same as the order of the matrix. So if we have an order 2 matrix, then you're going to have lambda 1 and lambda 2, which may or may not be the same. So if you have repetitions of a lambda, you do have to count them many times. So I'm going to go back to that afterwards. And the other condition is that the determinant of the matrix, just to clarify, determinant of A, the original matrix, so not the A minus lambda I, but just A, this has to equal to the product of the lambdas. So this is particularly useful for 2x2 matrices. It makes it much easier. But if it's an open answer question, if it's like the typical question where they ask you to find the eigenvalues, I would assume that they probably want you to do it formally. So they might want you to do it with the classic procedure with this equation. So this is more relevant for multiple choice questions. But in this case, notice how they do tell us that the trace is 0. So if we look at that first, then we know also that it's a 2x2. So if it's a 2x2, then we have 2 lambdas. So in this case, we can say that the trace, which would be the sum of the numbers in the main diagonal, so A and D, has to equal what we have here, which is 0. And this also equals the sum of the lambdas. And we know that one of the lambdas, one of the eigenvalues is -3. So we can just call this lambda 1, and lambda 2 we just don't know. So we know that A plus D is equal to 0. And also the sum of the lambdas is equal to 0. So if one of the lambdas is -3, then we know that the other one is 3. Now this part they actually didn't ask us to do, but they wanted us to find the matrix. We're trying to find A. So basically we're trying to find A, B, and D. And for now we can say that A would have to equal -D. So in this case, we can't do anything with the other part of the shortcut because we have no information of the determinant. You can't find it, of course, because you really don't know anything about these numbers. So that's just not going to really be useful, at least not yet. But the other piece of information we have is an eigenvector associated to this lambda. So as I was saying before, this is useless for the eigenvectors because it has no x in here. So that's not going to, you're not going to be able to use the eigenvector with that equation. But this one does, or this one. So the definition of the eigenvectors and eigenvalues. So I'm going to look at this one just because it's a little bit nicer to work with. And we know that our A matrix is ABBD. And we said that A equals -D. So I'm going to replace that. So I just replace A with -D. And then we're subtracting lambda I. Lambda for this eigenvector is -3. So I'm taking -3 times the identity matrix. Actually, sorry, it's -3. And the identity matrix is just ones in the diagonals. And all of this times our eigenvector, which we're told is -1, 2. Has to equal 0, 0. So we're going to end up getting a system of equations. So if we simplify this, this becomes +3. Essentially, you're just going to end up having that all of this just becomes 3003. So when you simplify, this becomes -d -3, then b -0, b -0, and d minus, I'm so sorry, wait, sorry, it's plus, -d +3, and then d +3. And then this times -1, 2 is equal to 0, 0. So if we multiply through, you're going to get a system of equations. So I'm just multiplying row times column. And that will become d -3 plus 2b equal to 0. And then the other one is going to give us -b plus 2 times d plus 3. So that will be 2d plus 6 is equal to 0. So if we simplify a bit, we can then do substitution or elimination, doesn't really matter. Maybe I would do elimination just because I can see here that if I multiply this by -2, that's going to give you a -2d. And then if I add that equation to the one below, the d part is going to cancel. So I think that's going to be a little bit simpler. So this will become -2d -4b 6. This one I'm just going to leave it. And then if we add them together, I'll just add a page here. If we add them together, we get these cancel. It should be -5b equals -12. So b equals 12 over 5. And then of course you can just substitute into whichever one and find d. So we should get d plus 24/5 equals 3. So if you put that in fifths, that'll be 15/5 minus 24/5 should give us -9/5. And now we can just go back to the matrix, which we had written previously as, sorry, -db/bd. And then we can just plug everything in. So this becomes positive. Then you have 12/5 here and here. And then the last one is negative. So just to summarize, in the end, the key things here are knowing the shortcut, because in this case, they told us a trace. So you have to know how the trace is related, not so much to the lambdas in this case, actually, but just actually how the trace is calculated. So in this case, it's actually just about knowing that the trace is the sum of the main diagonal. In other cases, they might ask you about the eigenvalues. So here it wasn't actually necessary, but you know that the sum of the eigenvalues has to correspond to the trace. So since we know that one of them is -3, the other one has to be 3. So that wasn't necessary, but in other cases they could ask it. And then the other big things here are just knowing the definition. So that can really be useful in different situations if they ask, if they give you information about the x's or maybe about the eigenvalues. And then for the eigenvalues, so usually the easiest thing to start with would be the classic equation that we use to find them. So in this case, it wasn't really necessary because we didn't need to find the other eigenvalues, but in other cases, it could be useful. Okay, if anyone has any questions, I muted everyone just to avoid background noise, but feel free to unmute yourself if you want to ask anything at any point. So I think we can go on. And the next questions I have are on differential calculus. This first one was from a past exam. It's not really hard, but it's just mentioning the Jacobian matrix. And I think the way that they asked it was a little bit confusing in a way. So first thing I just wanted to clarify is that a Jacobian matrix is not really anything special. It's just a when you take the partial derivatives for multiple functions. So they also had another exercise also in the past exams where they had something like f of xy equals, let's say 2x squared plus y, and then 3xy. So in this case, it's a function that maps R2, R2. And it just asks you to find the Jacobian matrix, which is really nothing special. It's just that you find the partial derivatives, essentially you find the gradient for each of these functions. So it's just a function that is actually defined through two functions. And you simply take the partial derivatives with respect to both x and y for the first one, and then also for the second one. So it doesn't really come up in exercises. I think in an exercise book, I didn't see any. But it did come up in a few past exams. So you just need to know what it is. And basically, we're going to take, in this case, it's going to be a 2 by 2 because we have two functions with 2 variables. It could have also been with 3 variables, though. So it could have been a 2 by 3. And you can think of it as if we call these functions, let's say g and h, then essentially going to have that the first row is going to correspond to g and the second row to h. And then here, you're going to put the variables. You don't actually have to write this, it's just to understand where you're going to put everything. And then since we're doing derivatives, we're going to be taking g with respect, we're going to derive g with respect to x, and then g with respect to y. And then same thing with h. So again, if you did have a third variable, it wouldn't be a square matrix, it would be a 2 by 3 in that case. So as usual, when you derive with respect to x, that means that you treat x as a variable and y as a constant. So the constant part goes away if it's added or subtracted. And then you derive this as you normally would. So you should get 4x. And then, just the opposite if you derive with respect to y. Now the x part is treated as a constant, and the y part in this case becomes 1. And then for h, if we derive with respect to x, now it's a product. So y is essentially together with the 3, it's part of the coefficient. So since x becomes 1, you're going to be left with 3y times 1. So 3y. And then for y, it's essentially the opposite. Now x is being treated as part of the coefficient. So now you're going to get 3x. Notice how it's not symmetric in this case, so it doesn't have to be. The only matrix that is going to be symmetric, assuming that we have continuous second partial derivatives, is the Hessian matrix. When I'm talking about derivatives specifically. So otherwise, these matrices don't have to be symmetric. And they might give you a point to plug in, a vector to plug in, so they might give you an x and y value, and then you simply plug them in. So it's not hard, it's just that you have to know what they mean by this. And we can actually say that the Hessian matrix is a special kind of Jacobian matrix. Because when you do a Hessian matrix, you actually start off with a function that is defined just through a single function. So maybe you just have this. And then when you do the partial derivatives, you get multiple derivative functions. And then you derive each one again. So we're going to see that with the next one. That's going to be more clear in a second. But just what I wanted to clarify is that the reason they really teach the Jacobian matrix is just because a Hessian matrix is a special application of it. So Jacobian is just when you have multiple functions to derive, with respect to multiple variables. And that's what we always do when we do a Hessian matrix, because you're deriving the gradient actually. So we can say that it's the Jacobian matrix of the gradient. So you're basically deriving the gradient. So that's what comes up in this question. So notice first of all how you have a function, and they should have put they should have made x bold here to indicate that it represents x1 and x2. But my point is that notice how, unlike the previous one, we have a single function here. We don't have multiple functions. The reason that they're still talking about a Jacobian matrix, even though when you derive this, you don't get, like, it wouldn't be called a Jacobian matrix, it would just be called the gradient, is because they actually want the Jacobian matrix of the gradient. So this is a notation for the gradient. And we want the Jacobian of that. And so, as I said before, when you do the Jacobian of the gradient, that's just the Hessian matrix. So my point is that all they're asking for here is just the Hessian matrix. So it's not really anything special. It's just that the way that they worded it was a bit confusing. Notice also how it's 2 by 2, so that also should be a hint that you're doing a Hessian, because the gradient is not going to be a 2 by 2. So it wouldn't make sense for them to ask you the gradient, for example, by itself. And before we do this, first of all, I would probably change the variables to x and y just to avoid getting mixed up. So we have y squared minus 2x, and then y squared minus x. And also, if it's not too complicated to multiply out, it probably is going to make it nicer to work with. Because otherwise, when we derive, we're going to have to use the product rule every time. And hopefully, instead, by multiplying out, we'll be able to avoid the product rule, at least most of the time. So I'm just going to expand. So I'm doing y squared times y squared. Then y squared times minus x. Then minus 2x times y squared. And then minus 2x times minus x, so plus 2x squared. And we can actually simplify the middle part. That's just going to become minus 3xy squared. And now it should be pretty straightforward to derive. So first, for the gradient, we simply derive with respect to each variable. So with respect to x, the x's are over here. And once again, you're treating y as a constant. So because it's multiplied by x, you can just think of it as together with the minus 3, in a sense that it's basically a coefficient. And x is going to become 1 when you derive it. So you're just left with the coefficient of minus 3y squared. And then here, it's just a classic power. So you're just going to get 4x. And now we do the same thing, but for y. So for y, we just get first 4y cubed. And then now x is part of the coefficient. So we keep the minus 3x. And then times 2y. So we can just simplify the last part. So notice how now our gradient is made up of two functions. If you had more variables, you would have had more functions. My point is that, just to relate it to the previous exercise, essentially this is your g and this is your h. You could also write this as a column. My point is that anytime we're doing a Jacobian, it's implied that we're deriving multiple things. So that's why they can call this a Jacobian, like what what we're getting next, which is a Hessian matrix, we can call it a Jacobian matrix, because now we're going to derive each of these with respect to each variable. And so we're going to get a matrix with multiple rows and columns, which is going to be your Jacobian matrix. So the Hessian is always going to be symmetric, assuming our function is continuously twice differentiable, which realistically it will be. I haven't come across any cases where it wasn't like that. So you should expect it to be symmetric. So first we derive with respect to, we can derive the first one with respect to x. So that should just be 4. And with respect to y, that's going to be minus 6y. So just to clarify. Similarly to before, it's like you have g here and h here. And then you derive with respect to x and y. Just to clarify, this was a derivative with respect to x and this y. Only reason I'm calling them g and h is just to relate it to what we did above. But you can also just call them f prime x and f prime y. So let's write that here. So this represents f prime xx, f double prime, sorry, xx. Now for the other one, we can derive with respect to x first, because x is in the first column. So we should get here for the minus 6xy, the y is being treated as variable, x is a constant. So again, x is part of the coefficient. So you should get minus 6x times 1. I'm sorry, I just dropped respect to, 1 second, sorry, I'm doing the wrong variable. So with respect to x, y is being treated as a constant, so it'll be minus 6y. Which also, of course, it is symmetric, so this has to be the same. And then with respect to y, we're going to get here 12y squared. And then now x is part of the coefficient, so we should have minus 6x. And then, of course, if they give you a point to plug in, which I don't think they did, then you would simply plug it into everything, and then you'd have your answer.
Excuse me, can I ask a question?
Yeah, of course.
Since it's symmetric, I think in the exercises, it was done in a different way, where like in the first column, it was like the first function derived with respect to x. Under that, it was derived with respect to y. And then the second column was for the second function. But since they're symmetric, it should be the same, or?
Wait 1 second. Yeah, exactly. So yeah, and it doesn't make a difference. Yeah, so yeah.
It doesn't really matter which way we do it?
Right, no, but for the other exercise, it did make a difference. So this should be the classic way. I would stick with this way just because then, you know, for this kind of question, it does make a difference because it's not symmetric.
Okay.
So yeah, no problem. Just wondering, did you see where did you see it done that way? Was it like from a professor?
I think it was the exercise book we were given.
Okay, then I'll check after just to see.
I'm not 100% sure, but I believe I went through it today and I believe I saw it that way, but I might be wrong.
Okay, well later if you want to send me a picture or tell me which where it is, I'll just take a quick look.
Okay, I'll take a look and I can send you a picture afterwards.
Okay, perfect.
Thank you.
Yeah, then I'll confirm. But yeah, the classic way is gonna be this one. Okay, and yeah, of course here I changed it to x. Sorry, I changed it to x and y just to make it easier, so we can change it back. But it's gonna be the same thing. So I think it's gonna be A. Yeah, A. And I would really recommend changing it to x and y because personally, I think it's so easy to make mistakes with the subscript. I think sometimes it's easy to think of it as a power. So personally, I would recommend that. Okay, so now I have an exercise on implicit functions. Let me just check. Yeah, we can do that one first. So the first part we might as well quickly look at because even though it's just a theorem, the idea is the concept is going to come up in the parts after. And also, if they're mentioning Dini's theorem, which is used to determine if your implicit function, if you have a unique implicit local function versus a global one, then I would expect that you probably have to apply it in part B. So notice how later they ask you first to consider if you have an implicit function in a neighborhood, so locally, and then globally. So the point is that when they say in a neighborhood, you can just use Dini's theorem. And then to analyze it globally, we can look at it different ways. But my point is that if they mention Dini's theorem, which is specifically for the local situation, I would expect that this kind of function is going to satisfy Dini, but then it's not going to satisfy it's not going to be a global implicit function, just a local one. So the idea with Dini is just that we can be sure that we have a unique implicit local function as long as the derivative with respect to y is different from 0, which graphically basically means that you don't have a vertical tangent at that point. So there was also an exercise in the homework where they gave you a graph of a function that was a circle or maybe an oval. In any case, the point is that anywhere you have or not necessarily a vertical tangent, but specifically where if you take a point and you look directly around it, your function is not going to pass the vertical line test in the sense that vertical lines will cross more than once. Then that guarantees that you don't have an implicit local function. And that would be where the gradient with respect to y is equal to 0. So at these 2 points, Dini's theorem is not satisfied. So we cannot find an implicit local function in a neighborhood of those 2 points. So think of it as you're looking at every point and you look directly next to it on the function if you pass the vertical line test. So you can think of it like that. And it's equivalent to saying that the derivative with respect to y is equal to 0. Then that's when it's not satisfied. So as long as our derivative is not 0, so at all these other points in this case, then we do have a unique implicit local function. Of course, I'm assuming the function is differentiable, but that's realistically not going to be a problem in these exercises. So now for part B, we have that this g function is being set equal to 0. And assuming that, because also we should be checking this first, assuming that this equation has solutions, then we just have to look at, again, the derivative if it's different from 0. So basically this value that we set it equal to, generally they call it k. And the point is that k has to be in the range of g. Just to clarify what that means, it's mostly a formality because it's really always satisfied. But if you think about a simple function like x squared plus y squared, if you try to set it equal to a negative number, like -4, even if you don't know the graph, the idea is that each of these is positive. So clearly here, your range of this g function is going to be everything from 0 to infinity. And -4 is obviously not in there. So this cannot give you a negative number. So if it can't give you a negative number, then we're not going to have an implicit function at all, let alone a unique one. So that's the first thing you should be checking, but realistically, it will be satisfied. It's just that you do have to find a way to make it clear that you checked that the value that you are considering is in the range. So either you find the range, or what's sometimes easier is just to think about it intuitively. For example, if I ask you, is it possible that x squared plus y squared equals 9? Even if you didn't know the range, you could see that, for example, if x is 3, and you plug in 3 for x and then 0 for y, that is going to give you 9. So you just have to find at least one combination of x and y that satisfies the equation. And usually it's pretty doable. Otherwise, you can try to find the range, but sometimes that can be a bit complicated. So here we're trying to set it equal to 0. So first we have to see if that's actually possible. So essentially 0 has to be in the range of this g function. Before we try to do the range, since again, it's not necessary, we can just try to see if there is a simple combination of x and y that is going to make this equation hold. And x squared and y squared is going to give you something that is positive. The e part by itself, that's going to also give you something that is positive, and specifically greater than 0. So with the minus sign, that's going to become negative. So intuitively, if this gives you a positive value and this is always a negative value, most likely there are going to be some x and y values that will make these essentially cancel out to give you 0. But we have to find a specific combination of x, y that makes that happen. And because we have an e here, putting in numbers here that are not 0 is going to get a little bit messy, because then you'd have, for example, if I plug in, let's say 1, 2. Then here you'd have 4e to the 2, which you can't, calculate really, and then it's a little bit annoying to work with. So since you have an e, the best thing is to pick x or y to be 0, just so that this becomes e to the 0, which is 1. And that's what's going to make it nicer to work with. So of course, we can't be sure yet that x or y being 0 will make this equation hold, but it's just something you can do to start and kind of see where it leads. So for example, if x is 0, then we have 0 squared plus y squared minus 4e to the 0. That's just going to be 4 times 1. And this is going to have solutions. Sorry, what did I write here? We actually have 2 solutions. So we can already see that there are at least 2 combinations of x and y that make this equation hold. And you could actually kind of easily see that if you switched it around and made y 0, you would also have the same kind of thing for x. So actually we have at least 4 solutions. Just to clarify, if this didn't have solutions, it doesn't necessarily mean that we don't have solutions in general, because I was, of course, making the assumption that x is 0. And then you can maybe try doing the opposite, try making y 0 instead, see if that has any solutions. And if that still doesn't work, again, it doesn't mean there aren't solutions, but you would have to analyze it further and try to find the range. So basically try to see what's the maximum value you can get from this, what's the minimum value, and then see if 0 is in between them. So basically, you could do this by using limits. But sometimes with limits, it can get a bit messy. You can get indeterminate forms. So it's better to avoid that unless it's really necessary. And from what I've seen, I think in most of the open answers, they usually make it so that you can easily find a solution. So it probably won't be necessary to use limits. So we already know that there are at least 2 solutions for this x value, and 2 solutions if you make y equal to 0. The point is that there are many solutions. And so the point is that this equation is possible. And as we said, we could also flip it around. And now we want to know if we have a unique implicit function. So we've established that we have an implicit function, which really just means that we satisfy the equation. So for now, we can say that there is at least one. Implicit function. And now we can use the Nice theorem, check the derivative with respect to y if it's different from 0. So if we derive this with respect to y, then the first part is a constant, so that will be 0. Y squared will become 2y. And then for e, when you derive e, you have to first keep it the way it is, and then multiply by the derivative of the inside. So this is the chain rule. So now I'm deriving xy with respect to y, so that should give me x. And we were checking specifically in a neighborhood of the point 0, 2. So at 0, 2, we're going to get here 2 times 2 minus 4 times 0, so that doesn't really matter. And so we're going to get 4. So the point is that it's not 0. And so according to Dini, the implicit function is unique. And also one little thing that I just noticed, if they give you a point, most likely the point is going to satisfy the equation. So I didn't even see that earlier. But you could have just plugged it in right away and seen that 0, 2 is a solution. Just make sure you realize that it's not necessarily the only solution. So now we want the Taylor expansion of the first order. So this is related to the tangent line equation. One little thing is that when they say Taylor polynomial, that's the same thing as a tangent line equation, in a sense that you don't have Peano's remainder at the end. But when they say Taylor expansion or anything else, then you do need to put Peano's remainder. So it's two slightly different things. So I'm just first going to write out the formula. So it's the same one you had in math 1. F of x0 plus f prime times x minus x0. And then we also need little o of x minus x0. But this is just notation. You don't actually need to do much with this. And I'm just going to make a note that if they ask you for Taylor polynomial, it would be without Peano's remainder. So they want the Taylor expansion of the first order at x0 equals 0. They also made a mistake in the answer, a very minor thing, but we're going to see what it is in a second. First of all, we can plug in 0. And also, even if they hadn't called it x0 and they had called it just x, make sure that you realize that's x0 still. So don't plug it in for x because that's supposed to stay a variable. You have to plug it in for x0. So since x0 was it 0? Yeah. We get f of 0 plus f prime of 0 times x minus 0, and then little o of x minus 0.
Excuse me?
Yeah.
Just a question, like, I don't understand, like, if, since we are, like, in R2, it shouldn't be, like, f of x0, y0, plus the gradient of Like we shouldn't put like both x and y.
No, because we're not doing a Taylor for this, for the whole function. It's just
Oh,
a Taylor for f.
Okay. Oh, okay. Thank you.
Yeah, no problem. So with these kinds of questions regarding implicit functions, they really can't, yeah, they really can't ask you for the Taylor for the whole function. It's always just for the f function, which is the y. So it's just one variable. And for f of 0, also, this is where they made the mistake that basically if x is 0, we've already established that when x is 0, y could be many things. So we actually don't know what y is because there's not a unique implicit function in general. And so you can also check by putting in 0 here. The point is that you're not just going to get one solution for y. So what they did was they took the same y value that they gave you before. But since they didn't ask you to do that in this part of the question, I'm pretty sure they didn't mean to do that because I've noticed also that Osimo most of the time, he just leaves this as f of 0, or you can just call it y. So my point is you should not plug anything in here because we actually can't know what this is, unless of course they tell you to specifically take the point 0, 2, and then 2 would be your y value. So there could be multiple values. So that part, we just leave it the way it is. And then for the derivative, for this, you need an equation that comes up pretty often with implicit functions, which is that for the derivative of f, you just have to take negative and then the derivative of x over the derivative of y. So we already did the derivative for y before. So derivative for y was this one. So 2y minus 4xy. And now we also need to derive with respect to x. So similar procedure. Now with respect to x, we should get 2x plus 0, and then minus 4exy times y. So kind of the opposite of what we had for the other one, in a sense that the x and y's are kind of flipped. So we can plug in our point. And also I was forgetting the minus sign here. And let's see, we're going to get 0 and then minus 4y e to the 0. And then for the bottom, we're just going to get 2y. Because the second part is going to be 0. Because it'll be 4 times 0. So even though we technically don't know y ends up canceling out. So we should get in the top 4y e to the 1, in the bottom just 2y, and then we're just going to end up with 2. So then if we plug that in, we have f of 0, which again we have to leave as it is. And then for the other part, we have 2 times x minus 0. So that's just going to be 2 times x. And then plus little o of x. So if the y part hadn't canceled, you would just leave it the way it is. So you would have something in terms of y also. Unless, of course, as I mentioned before, they had said, find the implicit function at x equals 0, and then they tell you that y is equal to 2. My point is, we shouldn't use that y value. So I know they did in the answer. But if they don't say to do that, I really don't think we should be using it. Let me just double check 1 second. Actually, sorry, let me just correct myself. I just realized they are referring to F specifically, which is what they mentioned before. Okay, yeah, actually, the way that they said it was f of x is specifically in this neighborhood. Okay, so we should be using that point. So if they hadn't said this, though, that's also possible. Then we wouldn't plug in the y. So I'm just going to plug it in now. Okay, so now for part C, we want to know if this implicit function is unique, not just locally, but also globally. You can look at this in different ways. The classic way to check that would be using the derivative of f and checking if it's always positive or negative, which would guarantee that the function is strictly increasing or decreasing with respect to y. Notice how our derivative function, though, is pretty messy to deal with. You can't really tell just by looking at it if it's just positive or just negative, but most likely it isn't, considering that yeah, probably if you plug in different values, you could probably easily get both kinds of numbers. So you could either show that for some x values, this gives you a positive number, and for other ones, it gives you a negative number, which would imply that the function does not satisfy the theorem for a unique global function. Otherwise, the easier thing to do is go back to what we did before. We already said that there are multiple points that satisfy this equation. And so if that's the case, then this isn't there isn't a unique implicit function automatically. So it's kind of like, for example, this situation, that there's multiple points in the graph that satisfy the equation. And in particular, if you check the vertical line test, it's not going to be satisfied for all of them. So it is satisfied for some of these points. So for example, in this little neighborhood, the vertical line test would be satisfied. But for these points, as we said before, it isn't. So you can explain it different ways, but probably the easiest would just be to say that there's many points that satisfy the equation. In particular, you have x's with multiple y's. So generally, when you have x's with multiple y's, then that implies that you don't have an actual function. So we could say that we saw that 0, 2, and 0 minus 2 were both solutions. And so basically that means that when you plug in 0 into the function, you get 2. But then here, when you plug in 0 into the function, you get minus 2, which doesn't make sense for a function, because with a function, you should be only getting one result. And so it wouldn't pass the vertical line test. So they do have to make it simple enough so that you can easily find two solutions, in particular with the same x value. And then you can say that a function cannot be like that. You can't have that the same x gives you multiple y's. Otherwise, as I mentioned before, you could try checking the sign of this, but that's just not really practical to do. So I would probably stay away from doing that, assuming that it's this complicated. But if you did have something simpler, like maybe x over y, you can easily see that this can give you any kind of sign, any kind of number, positive or negative. So the point is that as as X and Y change, you're going to get different signs, which means that the function can switch from strictly increasing to strictly decreasing. And then it doesn't satisfy the theorem. So there's several ways that you could do it if it's a simpler, if you have a simpler derivative here. Okay, so I think we have one more on, did you want to ask something?
I just had a question. You mentioned Pinot's remainder.
Yeah.
When did you say we need to use it, or like write it down?
Yeah, you just have to write it down. So this is part of the Taylor expansion. So since they asked you for Taylor expansion, at the end you have little o of x minus 0, which is just little o of x.
Do we always have to write Pinot's remainder?
Like the name, you mean?
No, as in like when we're finding the Taylor expansion.
Yeah, like this. You just need to write this. Yeah, little o of x at the end.
Oh, okay.
Yeah, so you don't need to mention it's Pinot's remainder or anything. It was just to know. And yeah, so you just plug in x0 here, and then it simplifies.
And excuse me, I don't really understand like the last part of the question. Yeah, this one. Like why? How did you find like two y and why it doesn't work?
So basically, this part we had before, that we saw that some of the solutions to this equation were 0, 2, which is, they actually mentioned that one in the text, and then 0, minus 2. And so that means that you put in the same x value, but y can be different.
Okay, thank you. And why did you cross it? It doesn't work?
Just because it doesn't make sense for a function, because with a function graphically, if you
Oh
try
yeah,
to,
you cannot have 2y. Yes. Okay.
Yeah, exactly.
Okay.
So yeah, you can think of it as if you try to graph it, it's not going to pass the test.
Thank you.
Sure. Okay, and one last thing also, since they did mention a point, and you have powers of 2. With powers of 2, anything, if you plug in a positive or negative number, like 2 or minus 2, you get the same thing. So when you see something like this, you should be kind of intuitively thinking that if you have even powers, it's very likely that you are going to have multiple solutions to that. It's just very likely. Of course, it also depends on the rest of the function, but usually you are going to have multiple solutions. So then you just, it's just a matter of switching the sign, for x or y. Okay, so now the next exercise is on unconstrained optimization, and we're looking for local and then global mins and maxes. So if it had been constrained optimization, then if you're checking for the globals, you can try to use Weierstrass's theorem. Weierstrass comes up pretty often. And that's when you have the classic situation is when you have a constraint or a domain given by x plus y squared equal to a number like 9, which graphically is a circle. This one you just want to recognize because it does come up a lot. And you just need to know that it's a circle, and specifically it would be a closed and bounded set. And assuming then that the function that we're dealing with is continuous on that set, then Weierstrass guarantees that we have both a global min and a global max. So if you see that, you can already guarantee global min and max. So they would have written something like, find the min and max of this function subject to the constraint x plus y squared equal to 9. Now here instead, we don't have any constraints. And also if you look at your function, there's no particular kinds of functions that have restrictions naturally, like logs or even roots or fractions. So x and y can be literally anything. And so our domain here would be all of R2 because we have 2 variables. So when you have this kind of situation, most of the time they don't ask you about the globals because usually we can't determine it, not with the methods that they teach us, unless it's a very simple situation where the Hessian matrix is super simple, in a sense that you find that it's always positive, definite, or semi-definite, or indefinite, or whatever it is, and it never changes to another type. Or you have another case where maybe the function is simpler than this, and you can easily find the range. So I would expect that it's more likely the first situation where the Hessian matrix becomes very simple. Also because a function is not particularly complicated. So it's just powers and numbers. So usually the Hessian matrix becomes pretty easy to analyze. So when you're checking for mins and maxes, the main kind of points that we have to check for are stationary points. But technically, you also want to check if you have exceptional points. That's more common though for constraint optimization, because that refers to boundary points, which you can't have here because our domain is all of R2. And also points where the function is not differentiable. But those realistically, you're really not going to see in this course. That was something that came up more in Math 1. So that kind of point you can only have with functions that are not differentiable. So usually piecewise defined functions, which again, you're not going to have, or something like with an absolute value or a root. But you really probably are not going to see that come up. It's just to keep in mind that those are technically possibilities. So for example, like something like this is a function square root of x squared plus y squared, has an exceptional point at the bottom. So this is not a stationary point because you have a sharp point of change. So it's not differentiable at this point, but you can see it as the lowest point. So it's the local and global minimum or minimizer. So anyway, you do have to kind of think about that, but realistically, those shouldn't come up. So especially for unconstrained optimization. So now for the stationary points, similarly to one variable functions, we just have to look at when the derivatives are equal to 0. So if we derive with respect to x, we should get here 2x minus 6 and y for y cubed plus 10. And then we just need them both to be equal to 0. So it doesn't really matter which one we start with. We should get x equals 3. And here we're going to get y cubed equals minus 5 over 2. And then we have to cube root that. I'm just quickly going to check the answer for that. Yeah, all good. So we have a single stationary point. So the fact that it's unique implies that it could be a simple situation, like the one I mentioned before, where the function is always maybe positive semi-definite or negative semi-definite or indefinite. The point is, usually when you have a single stationary point, it doesn't change. So now to figure out what kind of point it is, we would have to look at the Hessian matrix. And check again which type of situation it is, whether it's like positive or negative, definite or semi-definite or indefinite. So we can derive this with respect to x and then y. And we're going to get with respect to x2, with respect to y, 0. And then here with respect to x, you get 0. And with respect to y, you get 12y squared. So it's relatively simple in a sense that you only have a variable over here. Everything else is just a number. And at the beginning, we only care about the locals. So for the locals, we're trying to establish if the function is convex or concave at the point that we're checking. So at this point. So we can just plug it in. So we're going to have 2, 0, 0, and then this is going to be a little bit messy, but for now, I wouldn't worry about simplifying it, because if they make something kind of so messy, usually they have to make it so that in the end, you don't need the exact value, because of course you can't use a calculator. So for now, we can just leave that. And we have to analyze now the leading or northwest principal minors. So in the northwest corner, the first determinant you have is 2. So we can call this determinant A1. And then the next determinant we can get is all of this, so the whole thing. We only care about the sign, so we don't necessarily need to simplify this all that much, because in this case, it works out pretty nicely in a sense that you can see that when you square this, it becomes positive. And when you calculate the determinant, it'll be multiplied by 2, so still positive, and then minus 0. So we don't need to bother simplifying. So I would probably write out the determinant, but no reason to waste time simplifying. We can just say that it's clearly greater than 0 because of the power of 2. So the fact that they're both greater than 0 is equivalent to with one variable function saying the second derivative is positive, greater than 0 specifically, which implies the function is strictly convex. So just to clarify, I should have actually said this a little bit more clearly. When they're both positive, that initially means that that this is positive definite. So we say the Hessian matrix at this point at least, because we haven't checked the other points. And positive definite is what I was saying, is like saying that the second derivative at this point is greater than 0. And just to go over it really quickly, in order for it to be negative definite, it would have to be negative and then positive. So first figure out what type of situation it is, what type of Hessian matrix it is, and then you can associate positive definite to the second derivative being positive for a one variable function, or negative definite, it would be negative. So it implies the same thing about the function, that at this point specifically, the function is strictly convex. So if you think about a strictly convex function and you have a stationary point, it would have to be at the bottom. So that makes it a local min.
And
So sorry, go ahead.
no, I was just asking, like, how do we know if it's like semi-definite positive? I think it should be like a 0. Like, is it like the coefficient of the matrix who are equal to 0, or it's the determinant of the minors?
Yeah, so if you had gotten that one of these at least was 0, then it might be
Yeah.
positive semi-definite.
But
Yeah.
it's one of the coefficient of the matrix.
Do you mean one of the numbers in the matrix?
Okay, not the determinant.
Wait, no, I'm sorry. By coefficient, were you referring to the numbers in the matrix? Or
Yeah, the coefficients are the numbers in the matrix.
no, that doesn't tell you by itself. Because it could be
Okay.
positive. You have to look at the leading principal minors, and then if you do get any zeros, you then have to analyze all the principal minors. So we're actually going to see that with the next part of the question.
Okay, perfect. Thanks.
Yes. And it's unlikely to happen though with the locals, usually at least, because if you did have that this was positive semi-definite, that's now the equivalent of saying that the second derivative is greater or equal to 0 at this point. And so if you think about a one variable function, because it's easier to understand, basically this implies that it could be equal to 0 or it could be 0. And that by itself doesn't tell you anything, because when a second derivative is 0, graphically it could be any kind of point, in the sense that it could be something like x cubed that has a second derivative is equal to 0 at this point, and it's not a min nor max. Or it could be something like x to the 4, which is a min, or it could even be something like minus x to the 4. So my point is that think of it as, we're basically saying that in this case, we can say the function is strictly convex at the point. Here we could say that it's convex at the point. But saying convex at the point also means it could be horizontal. And so the point is that it doesn't guarantee anything unless you analyze the rest of the function. So that's why that's called a necessary and not a sufficient condition. So having a positive semi-definite Hessian matrix at a specific point doesn't guarantee anything. It could be a local min, but we can't be sure. Versus if we find that it's positive semi-definite for every single point, not just at one point, then that's the equivalent of saying that a function is always convex. And always convex could be like a parabola, or theoretically could even be a straight line, which is both convex and concave. The point is that this would still be, whatever point we're looking at, is still considered a local and global min. So the point is that positive semi-definite at a specific point doesn't guarantee anything. Same goes with negative semi-definite. But if instead it's for the whole function, then you can say that that it's not just a local, but even a global min in the case of positive semi-definite. So that's actually what's going to happen here, because now they ask us if they're also global. So to try to determine that, we can look at the Hessian matrix in general. So basically, we're looking at the Hessian matrix for all xy, which means I'm going back to this one. So we're only doing it because they're asking us about the globals. Otherwise, you wouldn't bother if they had only asked about the locals. And if you redo the leading principal minors, we have that for A1, it's going to be 2. For A2, it's going to be the determinant, which is going to be 24y squared. Because you have an even power, no matter what y is, this is going to be greater or equal to 0. So if it had been greater than 0, we could say it's positive definite. The problem is that it could be 0. And so when you have that, it can be 0 at some points, there is a possibility that it's indefinite. So my point is, we can't guarantee yet that it's positive semi-definite. We would have to analyze all of the principal minors in that case. So anytime you get zeros, if there's a possibility that it's positive semi-definite, or in other cases negative semi-definite, then you have to analyze it further.
But how can we analyze further? Because like there is normal coefficients in the matrix.
Yeah, so we analyze all of the principal minors, not just the leading ones. So that means that we take all the determinants of order 1 and order 2, where we cross out the same rows and columns. So this number we got by crossing out the last row and column. If we crossed out the first row and first column, we would get 12y squared, which once again we know is greater or equal to 0. So far, all of the principal minors are greater or equal to 0. And then for order 2, the only one you have is the one we've already looked at, which we already said was 24y squared. So for order 1, it's just the numbers in the main diagonal in the end, because it's what you get when you cross out the same row and column, or sometimes in other cases, same rows and columns, plural. And now we can see that all of these are greater or equal to 0. So you do technically have to do this extra step, because in other cases, it is possible that maybe this was negative, in which case we wouldn't satisfy positive semi-definite. We also wouldn't satisfy negative semi-definite, because for that, we would need these ones to be less or equal to 0 and needs to be greater or equal to 0. And then it would be indefinite. So the point is that when you get 0, there's the possibility of indefinite. And so that's why you have to analyze it further. Is that more clear now?
Yeah, thank you. But so here it is a semi-definite positive.
Yep.
Okay.
And so we're saying that it's always positive semi-definite. Also, it's best to make it clear that it's not definite for all the points, because when we say semi-definite, it could also be definite. in general. But here we already know that if y is 0, for example. Oh, sorry, 1 second. Yeah, if y is 0, this would have been 0. So the point is, you want to clarify that it's positive semi-definite and not definite. And this implies that the function is convex, so not strictly necessarily, but it's convex. For every point. And so then that stationary point that we had has to be at the bottom, or again, it could theoretically be a function that looks like this. In any case, it would be not just a local, but also a global min. So whatever point we found before, I think that was it, is a local and global min. So also with positive semi-definite, usually you can't guarantee that it's strong, meaning that in the neighborhood it's the only one. But in this case, we've already established that it was the only one. So you could also say that it's strong. So in this case.
Can you repeat how do we say why it is a global min?
Yeah, so basically after you figured out that it's a local one, you have to look at the Hessian matrix for the whole function. So before you plug anything in, basically, and you start off looking at the leading principal minors again, because now we're basically trying to figure out if the function is convex or concave for all points, not just at that one point. And if you had gotten, for example, that these are both greater than 0, then you could already say that the function is positive definite. Sorry, the Hessian matrix is positive definite, so the function is strictly convex. So graphically, it's something like this. And then your stationary point would be a global one. Because we're saying that it's strictly convex the whole time. So if it's like that, essentially the function is not going back down, which means that you can't have lower points than the one that we're looking at.
Okay, so to understand if whether they are global one, we have to understand if they're convex or concave.
Yeah, exactly. And so if you had a situation where the Hessian matrix changes type from like positive to negative, then you can't make a conclusion. And that's why most of the time they don't ask, because a lot of times it does change and then you can't make a conclusion.
Okay, thanks.
And I'm just gonna make a note here that if in general a Hessian matrix is positive definite at a specific point, notice it's easy to kind of overlook this, but notice how here I'm writing x0 and 1 sec. Here I wrote x comma y. So this is the general Hessian matrix versus this is at a specific point. So if at a specific point, it's positive semi-definite, let's say. And the gradient at the point, or let's just say x0 is a stationary point. Then we can't conclude anything. So it's a bit tricky, but it's actually the same thing as one variable functions. That if you know that at a certain point, the second derivative is greater or equal to 0, that by itself doesn't guarantee anything. And this is the equivalent of saying that the Hessian matrix is positive semi-definite at a certain point, then you can't say anything. But if you know that it's always positive semi-definite, then it is always convex. So just think of it as when we say convex versus strictly convex, it could also be, for example, a horizontal line. And so after, if you know that it's convex at a point, maybe it's horizontal, and then later the function goes down like that, or maybe other way around. So my point is, in both cases, this could have been positive semi-definite at like this point in the middle. But in one case, this is a local max, and in the other case, it's a local min. So the point is that if you only know locally that it's positive or negative semi-definite, that doesn't guarantee anything. But if you know that globally, so for all the points, it's positive semi-definite or negative semi-definite, then you know how the whole function looks, and then you can make a conclusion. So for the locals, it's unlikely to happen, like to see that situation, just because again, you can't make a conclusion. But for the globals, it can happen, and you can make a conclusion. Okay, any more questions?
Yeah, like if it's like the Hessian at x0 is semi-definite, can we say it's a local minimizer or no?
No, because that's like what I was saying, that
We have to
They-
look also at the Hessian at x in
Sorry?
general. We have also to look at the Hessian in general,
Yeah,
not only at point x0.
exactly.
Okay.
And if you want to look, kind of understand this in more detail later, it might be helpful to think about this in relation to one-variable functions. So just think of it as, this is like saying that the second derivative is greater or equal to 0.
Okay, thank you.
Yeah, no problem. I think the best thing is to relate it to one-variable functions, because if you know the examples for that, like the specific situations for that, it just helps to understand it. I'm just gonna quickly write it down. But for example, if you have like x to the 4, which is like a parabola, I mean, it is a parabola. If you actually do the derivatives, you find that of course you have a stationary point at 0. Because you got f prime of x is 4x cubed, f double prime is 12x squared. In both cases, when you plug in 0, you get 0. And my point is that without knowing the graph, this by itself doesn't guarantee anything. So basically, this just means that the function is convex at the point, but it doesn't guarantee anything about the function in general. Because it could have also been the opposite, like minus x to the 4, it would have been almost the same thing in the sense that, again, you would have had that the second derivative is equal to 0 at that point, but in that case, it becomes a local max. So the main thing that I think helps is just to think about the fact that when a second derivative is 0, it doesn't allow you to make a conclusion if you know that it's 0 at a certain point. Only if you can be sure that it's always greater or equal to 0 or always less or equal to 0 for every single point, so globally, then you can make a conclusion. So the point is that, yeah, so you need to just analyze it in general. And then you can see like here, for example, that if you think about the fact that there's a power of 2, this is always going to be greater or equal to 0. And this is always going to be less or equal to 0. So then from that information, you can say that the function is always convex and always concave, and then you can make a conclusion. So yeah, basically, if it's semi-definite at a certain point, you have to then analyze the rest of the function. That's kind of the summary of all of this. Okay, so sure, no problem. So now we can look at the integral ones. Let me just think if we should go through all of them. Okay, yeah, shouldn't be that bad. So the first part is applying the theory of Riemann integrals. So with the upper and lower integral sums. Yeah, just upper and lower integral sums. So I'm just going to skip ahead to part B because the first part is just just one of the proofs. We don't have to graph it, but what they usually do with these kinds of exercises where you have to calculate upper and lower integral sums is they make the function either very simple to graph or at the very at the very least, they make it so that it's obvious that it's either increasing or decreasing. In this case, you have x from 0 to 1, and then you have 2. So this is increasing even though it's not strictly increasing. And I'm just going to mention why that's relevant in a second. And so now, if we're calculating upper and lower integral sums, we're going to have to find the infimums and the supremums in each of those subintervals that they give us. And in this case, since the function is increasing, no matter which subinterval you're considering, let's say you take the first one, 0 to 1/2. So we're just taking this portion of the function right now. Then you can see that the lowest point is the endpoint on the left, and the highest point is the endpoint on the right. So the infimum is the value of the function at 0, and the supremum is the value of the function at 1/2. So my point is, we can just immediately say that all of the infimums, which we call lowercase m, are the points on the left, and then the other ones on the right. So we're going to use these points for the lower integral sum, and then the other ones for the upper. So it's useful to realize that it's true for any increasing function, not just this one. And of course, decreasing it would be flipped around, because this way, if you got a function that you can't graph, but maybe you know by somehow maybe using derivatives that it's increasing, then you know which ones are going to be the infimums, which ones are going to be the supremums without needing the graph. So we have our subdivisions here given by these numbers. In this case, the interval lengths are not the same. They don't have to be. And we just need to calculate the two sums and then do the subtraction. So if we start with the lower integral sum, you're really just doing a bunch of rectangles, finding the areas of them, and then calculating the sum of all of the areas. So formally, we're doing a sum of the infimums times the change in x. So for example, we have 0, then we have 1/2 and 3/4, and then 5/4. Those are our points. So for the lower integral sum, you're going to take the infimum of each interval and then draw a rectangle. So since it's the points on the left, you're going to get something like this. My point is, it's going to be an under approximation of the actual definite integral. And then with the upper integral sum, we'll get an over approximation. So this is just taking the areas of the rectangle. So you're just doing the height times the length, length times height, which is regular area of a rectangle. And so for the first one, the height is m1. I'm just going to write it formally for now. And then the length would be the difference between x1 and the one before it. So x1 and x0. And so on. As we said, the infimums, or the mi values, are the points on the left. So that's what you get when you put in the first point into the function. So that's going to be f of 0. And then you take the change in x, which is the difference between 1/2 and 0. Then for the next interval, the left endpoint is 1/2. So we take f of that to get the corresponding value on the function that we're going to use as a height of the rectangle. And then we multiply that by the length of that rectangle, or of that interval, which is now 3/4 minus 1/2. So basically we did this one, then we did this one, now we do this one. So once again, we take the one on the left, we plug it into the function. and then times the length of that subinterval, which is 5/4 minus 3/4. And then finally, the last one, oh, I'm sorry, wait, yeah, the last one is gonna be 5/4. And the length of that is gonna be 2 minus 5/4. So notice how in the end, to find the infimums, we need to plug in 0, 1/2, 3/4, 5/4. We're not gonna plug in 2, because we only care about the left endpoints. So make sure you don't accidentally do an extra calculation. But also intuitively, if we split it up into 4 subintervals, we should have 4 calculations here. So if you had accidentally kept on going, you might realize that you did one more calculation than you should have. So in the end, it's just length times height. The notation, I think, kind of overcomplicates it. And it's really just about understanding what you're using as the height. So the point is that if it's increasing, it's always the point on the left. And now we just plug in all of these points, 0, 1/2, and so on into our function, which was first x and then 2. So if we plug in 0 into x, we just get 0. Then we plug in 1/2. So we get 1/2 times the difference of 1/4. Then we plug in 3/4 again into x. And then finally plug in 5/4, which now goes here. And then of course we just simplify. So now it's the same kind of thing for the upper integral sum. Just that instead we're taking the points on the right. So we call those the capital M values, because these are the supremums. So now instead of using these 4 values, we use these 4 values. Other than that, the calculation is the same. So it's just that first one you plug in is 1/2. The difference that you multiply by is the same. So the length of the first subinterval is the same. Only difference is the height, because basically graphically we're just taking the point on the right rather than the point on the left, but the length is identical. So everything else is the same. I'm just gonna skip ahead to the answers here just so we don't waste time doing all these calculations. Just 1 second. Okay, so you got 2 for the previous one, and then 47/16, which is approximately 3, a little bit less. And then they just ask us to verify that the difference between them is less than epsilon, with epsilon equal to 1. So epsilon just, or not epsilon, but the difference between them just refers to the difference in the approximations. So the smaller that difference is, the closer these are to being equal to the definite integral. Basically the idea is that if we want this difference to get smaller and smaller, we should pick more subintervals to make the approximation more accurate. So we're simply taking the difference between them. Which is going to be 47/16 minus 3. So if you put that in minus 2. If you put that in 16ths, that's 47 minus 32/16, so 15/16, which is in fact less than 1. So they just picked 1 as a kind of random number. Could have been something else. So it's not that generally this has to be 1. But the idea is that if we take more and more subintervals, this difference should be getting smaller and smaller, so it should be approaching 0. And now for part C is just with a different function, and it's kind of the opposite question, where they give us the function and we want to find a pi, so a set of x values that we can use for the subintervals to make the difference again less than 1. So they actually kind of tell you what to do here as a hint. So first I'm just going to show you though, in case they didn't do that, how you could get an idea of what to pick. And if we just kind of rewrite this, you have x equals n over 3 for those n values. So that just means that it's for when x equals 0 over 3, so 0. Or 1 over 3, 2 over 3, 3 over 3. So I'm just plugging in those n values. And so in the end, they're telling you that your function is 1 for those x's. For any other x is equal to 0. So for all the multiples of, I'm sorry, what did I write? Sorry. It was divided by 3, sorry. 1/3, 2/3, and 3/3. So for all the multiples of 1/3, including 0 and 1, you get 1. Otherwise, you get 0. So basically we have 0, 1/3, 2/3, and 1, which all give us 1. And everything else in between is going to be 0. So if they ask us to make it so that the upper minus the lower integral sum is less than 1, basically we want the approximation, the two approximations to have a difference of no more than 1. And if you think about the possible values for the upper and lower integral sum, if you think about the most kind of extreme situation where you actually don't split it up into subintervals, you take a single subinterval, then if you take a single subinterval, the maximum of the upper integral sums, so this would be the supremum, that would be if you use the highest of the heights as the height for the whole rectangle. So if I were to take a rectangle with this height, which is a height of 1, and a length of 1, then my area would be 1 times 1, so 1. If I took the lower integral sums, the lowest of that, so the infimum of it, would be if I take the lowest value of the whole function as the height for the whole rectangle, and the lowest value is 0. So if you take, a height of 0 with a length of 1, that's going to be 0 times 1, so 0. And so my point is that the maximum difference between the two is 1, no matter what. And we want specifically the difference to be less than 1. So if, for example, you split the interval into 2, let's say. If you split the interval into 2, then you can see that in both of the subintervals, you have 1s and 0s. So for the left part, when you do the upper integral sum for starting with that part, the supremum would be once again 1. And so basically it would also be the same for the other one. So my point is that in each of the subintervals, the supremum would be 1, which wouldn't change anything. It would give us exactly the same result. So what we want to do is make it so that either this becomes smaller or this becomes bigger, so that the difference becomes lower than it was before, since that's what they were trying to get us to do. And you can't actually make this any bigger, because the infimum is always going to be 0, no matter what subinterval you take. Even if you take, for example, let's say this subinterval, the infimum is 0. Or if you take this one, infimum again is 0. But the supremum can change, because if you take, for example, this subinterval, then the supremum and the infimum, they're actually both 0. So basically what we want to do is we want to pick subintervals that do not all contain these points. So later we can also do what they suggested doing, but another option is to do something as simple as, for example, let's say taking 0, one second, what's the number? 1/5 and then 2/5. just gonna show you how to take those numbers after. And then you can skip ahead to 1. So the reason I picked them like this is because if you look at 0 to 1/5, 0 to 1/5 does contain one of those points. But 1/5 and 2/2, which would be, oh, sorry. Should put different numbers. Sorry, I have to do something like 1/10. Okay, so 1/10 and 2/10, which are 0.1 and 0.2. So they're both over here. My point is that in that subinterval, your infimum and your supremum are both 0 because you don't have any of those points. So basically, I was just trying to make it so that at least one of the subintervals doesn't have those higher points, so that the supremum is going to be lower. And so now what's going to happen is that when we take the upper integral sum, for the first interval 0 to 1/10, your supremum is 1, and your length is 1/10 minus 0. But then for the next one, 1/10 to 2/10, your supremum is actually 0. It's the same as the infimum. And the length is this. And the last one, your supremum, for the rest of it, the supremum is 1. And the length is 1 minus 2/10. So because this part is 0, it's going to make everything a bit smaller than 1, because you're going to get 1/10 plus 0, and then plus 8/10. And so we get 9/10. And meanwhile, for the lower integral sum, you're actually always going to get 0, because no matter what subintervals you take, you always have that the infimum is 0. So it's 0 times anything is going to give you 0. And so now when we take the difference, it's going to be 9/10 minus 0, so 9/10. So the point is that what can be useful here to try to figure out what subintervals to take is think about what's the absolute highest upper integral sum and what's the absolute lowest upper integral what's the highest upper and the lowest lower one. See what that difference is. So see the highest maximum difference you can get. And then you're trying to make that smaller, which means that you either need to make it so that at least one subinterval doesn't have a high supremum, or at least one doesn't have a low infimum. And the only way to accomplish that here is to, again, to pick subintervals that don't include the high value of 1. And just to understand what they did, they didn't say that you had to do it this way. Or, of course, if you have a hint, you might as well use it. But I just wanted to show you that in case you don't have a hint. They tell you to use the points of type n/9. So basically here, they're trying to tell you that if you take the 9ths as the values for the subintervals, you should get something that is also, in the end, going to have a difference that is less than 1. And that's because if you do take the 9ths, then at least some of those are not going to include those higher points of 1. So if you actually write it all out, for example, here, 1/9 to 2/9, we know that this is equal to 1/3. So basically, on this interval, the function is equal to 0. There are no 1s. So that means that both the infimum and the supremum here are going to be 0. So it's the same kind of situation that I had here. So there's, many ways of doing it. And if you have no idea, like in case maybe the function is not so easy to kind of think about, you can also just maybe choose a certain number of subintervals to start with, like, I don't know, 2 or something, just to keep it simple, and see what the difference is. And if the difference is too big, so you need the difference to be smaller because they ask you to make it smaller, then just take more and more subintervals. So the other option is just to take a huge number of subintervals, but of course, if you have to do the calculations by hand, that might not be practical. So that's why it's useful to be able to kind of think about it like this.
Excuse me, I don't understand why you took the sup of S and the inf of I, because we usually do like
Yeah,
of S and sup of I, so
right. It's not, it's just because I was trying to understand the maximum difference, what that could be. Yeah, it's not something we usually care.
why do we need it?
Well, it's just to understand, because since we're trying to analyze, like we're trying to make it so that the difference is less than something. First, I'm just trying to see what's the absolute biggest difference I can get. Is that like more than 1 or not?
Mhm.
And then this can give you an idea of how to approach it. So like in this case, if you see that the difference is 1, then you just need to make it a little bit smaller. And so my point is that you just need to make it so that one of those points is not included in a subinterval.
Okay.
So so usually we don't care about the supremum of the upper integral sum and the infimum of the lower one. Usually it's infimum and supremum. That's for something else. Here we're just looking at the max difference. The point is that it's a very simple kind of function where you can kind of think about it intuitively. That's why I was doing it like that. So I just think of it as like I'm basically doing the biggest over approximation I can get is this. And the smallest is this. That's essentially what I was doing.
Okay, thank you.
Yeah. But you don't have to, write a formula or anything. It's more about the intuition.
Okay, thanks.
Sure. Okay. So let me just maybe see if we should skip something. Okay, maybe we can look at this one just because it's more relevant. And just to warn you guys, I think because I set the meeting for like 2 hours, so I'm not sure if it's going to automatically end after 2 hours, but if not, then we can keep on going. So here we have an integral, we're looking for an integral function. And it's for a piecewise affine function. In this case, with initial point 1. So we could graph this, although it's not absolutely necessary. It's just to kind of visualize what we have to do. We have first just 5 up to x equals 1, and then 5 over x, which is some sort of a hyperbola. And when you plug in the point of change 1, you get 5. So that tells us that it's going to be continuous. And the reason that's relevant is because if little f is continuous, it guarantees that big F is differentiable. We can actually apply the second fundamental theorem, which guarantees that. And also we can guarantee that f prime is going to correspond to little f. If instead little f is discontinuous, technically anything could happen, but usually big F would not be differentiable. So we're looking for the integral function. The best thing to do is to first just write down these inequalities. And then test a value in each of these into the integral function and think about what you have to do graphically. So for example, here, I could take an x value of 0. That's going to go in the integral function, which means we'd be integrating from 1 to 0. And you can have the numbers like that. It just means that you're going in the opposite direction. So you would get the opposite sign of what you get when you integrate from 0 to 1. But it doesn't really matter for now. The point is that graphically, you're starting at 1. And you're integrating to 0. So if you had gone from 0 to 1, you'll get a positive value. Because we're going actually from 1 to 0, it's going to switch signs, so it'll be negative. So you kind of get the opposite of what you would normally get, in the sense that the sign switches. But the point is that we can see clearly that with this example, you only have to integrate this part of the function, which was 5. So in my example, we have to integrate 5 from 1 to 0. And so that would become 5t from 1 to 0, which is just going to be 5 times 0 minus 5 times 1. And notice how it's negative as expected, because if you had gone from 0 to 1, it would be positive since it's above the x-axis, and now it switches. Now, this was just an example. We don't actually know what x is, we just know it's less than 1. But for any x less than 1, it's going to be the same kind of situation, in the sense that you're integrating from 1 to a number, which is to the left, and that means you're only going to integrate the left function, which is 5. So we always start from 1 because that's where they tell us to start. But now to generalize, instead of going up to 0, which was just an example, we actually go up to x. So basically, the best thing is first pick an example and visualize graphically what you have to consider, because it's not always so obvious. And then just replace your number back with x. So now if we look at an example for the next case, I'm not going to pick 1 just because then it would be the integral from 1 to 1, which it's kind of obvious. I'm going to pick something like 2, just so we can visualize it more nicely. And then we'd be integrating from 1 to 2. So from 1 to 2 means that you're just looking at the right side. So that's the function 5 over x, which I'm just going to change the variable to t. And you're starting from 1, and again, you change, or sorry, first we're just going to calculate it with 2. But the final answer doesn't matter too much. What matters is that we just have to integrate the right side. And as I said, this was just an example. So if we want to generalize, we don't actually know what x is. We just know it's bigger or equal to 1. But for any number bigger or equal to 1, when you plug it in here, you're always going to integrate that same part of the function. So to generalize, we can say that we go from 1 to x, and now we integrate this one. We just change the notation to t. So even though it might seem kind of obvious that you integrate 5 and then you integrate 5 over t or 5 over x, it's not always like this because it all depends on what you have here. So there are cases where when you take a number less than 1, you actually have to integrate both parts of the function. Or in the other case, you have to integrate both. The point is anything can happen. So that's why you want to have a general method to do it, because this is kind of a simplified situation, but it can be a bit more complicated. So maybe afterwards, I'll do a quick example with a more complicated case. So then we just integrate normally. This is just going to become 5t from 1 to x. So we just get 5x minus 5. And for the other one, we can bring the 5 out. And this is going to become 5 ln. So this will become 5 ln 5. I'm sorry, why did I put a 5 here? 5 ln of x in absolute value. Minus 5 ln of 1, but ln of 1 is 0. And since we know here that x is greater or equal to 1, we can take away the absolute value. So our integral function is going to be 5x minus 5, and then 5 ln x. And just to see the setup, in case this number had been different, I'm just going to change it to 0, for example. You start out the same way, so you just copy the two inequalities, and then again, you just test an example. So if you test, for example, something less than 1, I'm not going to pick 0 because 0 is a starting point, so then it's not really clear. So let's pick maybe -1. If you're integrating from 0 to -1, then you're starting here, and you're going to the left, which once again means you take just that first function. So this part's not too different. So we're integrating again the first function, which is 5. And same idea that we're starting from 0, but now -1 is just an example. Actually, we're integrating up to x. But for now, it's not very different from what we did above. Now, the second part, though, is significantly different, because if you take a number like 2, let's say, and you plug it in, now you're integrating from 0 to 2. And if you think about it graphically, that means you have to go from here up to 2. And that means you have to integrate both parts of the function. So this is why it helps to visualize it, because then it really makes it clear what you have to take and on which intervals. So we have to go from 0 to 1, and then from 1 to 2, for my example. But again, because we don't know if it's actually 2, we're going to change it back to x. So there isn't like a specific pattern that you can memorize. You have to always test an example in each case and try to visualize it. You don't need to have a perfect graph, but it's just to understand whether you have to take one part or two parts of the function and on which intervals. And then the integration is very similar. Once again, because the original function was continuous, big F will be differentiable, and automatically the derivative will equal little f. So they ask you to check whether it's differentiable. Technically, they probably want you to actually do it, but we already know that if little f is continuous, the derivative of big F is just going to be what we started with. So if you were to derive for either one, doesn't really matter which one, because we're going to get the same thing. We would get, for the first part, the derivative would be 5. Second part would be 5 times 1 over x. Now, technically, you should be removing the equal sign, because whenever you have a piecewise defined function, at the point of change, you have to consider both the left and the right derivatives and check if they're the same. So for the left derivative at 1, just to avoid having to use a formal definition of the derivative, you can just plug it into the left side of 1. And for the right, you get 5 over 5, which again is, 5 over 1, which is 5. So the fact that they're the same means that your derivative at 1 does exist. And so actually, we do have a derivative also at that point of change. So the final answer here would be that you have 5 and 5 over x, and you can put the equal sign for either one, doesn't matter which one, because a function is continuous anyway. So I'm just going to put it for the second one, just so it's consistent with what we had at the beginning. But keep in mind that when it is continuous, the equal sign, you could have put it there, and that's fine as well. It's still the same function. So if little f had not been continuous, then most likely what would have happened, it does technically depend, but usually this is what happens, is you would get different left and right derivatives, which would mean that you don't have a derivative at that point. And so then at that one point, there would be no derivative. So there would be no equal sign here. And so therefore, this would not be exactly the same as the original function. So the point is that when big F is not differentiable, it's going to be a very minor difference, but you're going to have that, you're going to be missing an equal sign for the two inequalities. So basically, you're not going to have a derivative at a specific point. But as I said, in this case, we could have just said that using the second fundamental theorem, we could guarantee that that big F was differentiable. Any questions on this so far? Okay, so let me just see what we have left. Okay, the last few are pretty quick, so this shouldn't take long. So for this one, notice how they are talking about a function that you're integrating on an unbounded interval, and then afterwards they have the integral of the absolute value. So anytime you see that you're dealing with improper integrals, which are also called generalized integrals, and one of them has an absolute value inside, this should make you think of the absolute convergence test, which says that if an improper integral converges absolutely, which means that it converges with the absolute value, then it's also going to converge without, which is called simple convergence. The other way around, though, is not true. So basically saying that it converges with the absolute value is a stronger statement than saying that it converges without.
The other way around, it would be true with divergence, right? Like if the absolute value was
we
in
don't
front
have
of
a
the
rule.
interval, in front of the integral, and then we said if that would diverge, then the one with the absolute value inside would diverge as well, right?
1 second, let's see, this one is, yeah, you could use, the properties,
Yeah,
because
it's the
this is-
sandwich rule again. Like if we have one function greater than the other one, here taking into consideration that the one with the absolute value inside of the integral is bigger than the one with the
Yeah, I
outside.
mean, you can kind of think about it like that. So are you thinking about the comparison theorem? Is that what you're thinking with bigger and smaller?
Yeah, exactly that
Yeah,
one.
just to clarify, technically you can't use that because the comparison theorem requires a function to be positive. Otherwise, you actually can't use it. But informally, you can think about it like that, honestly. The only reason I'm just being so specific is because they did have a trick question one time. Maybe this was in Math 1, actually, because this is related to series, where they said something like, is it true that if f of x is smaller or equal to g of x, then if g of x converges, f of x converges, which is almost a comparison test on like 1 to infinity. But the problem is that you don't actually know that that these functions are positive, and so that's what made it false. So my point is that technically, to use a comparison test, you have to actually know that functions are positive. So here we can kind of informalize it and say that it's kind of like that. But my point is that you should be checking actually if you're going to use a comparison test. And so here you technically can't. And that's actually why we kind of have this test, because otherwise you would just use the comparison test. And you wouldn't need an extra test specifically on this. So let's see, we can also say that if it converges absolutely, then when you remove the absolute value, it can only become smaller or equal to. So it converges to a value which is smaller or equal to the one that you had with the absolute value. And just to clarify, I should have written here that we're integrating from a to infinity. So notice how here they're actually telling us kind of the reverse, that the function without the absolute value converges to 6. So this is actually looking at it like this. And so we cannot guarantee that that with the absolute value is going to converge, because it doesn't work in that direction. So we cannot say anything regarding convergence or divergence. It could do either. But intuitively, we can actually just say that if without the absolute value, the integral is 6, with the absolute value, whether the absolute value is inside or outside, it can't possibly become smaller. So we can be sure that with the absolute value, it's going to be at least 6. And it could still be 6 because maybe the function was actually always positive. So maybe when you take the absolute value, nothing changes. Or maybe it wasn't always positive, in which case it could become bigger. But the point is that we can't guarantee that it converges. And just, this was from a past exam before they changed the syllabus, so a few years ago. But they can definitely ask this kind of question. And so notice how none of them is correct, actually, because this doesn't have the equal sign. So just keep in mind that when you take an absolute value, it doesn't necessarily become bigger. It could actually stay the same. So this one ended up being none of the preceding. And it's related to the next exercise a little bit. This one, I have to also change the way that they ask the question because they used to use a slightly different definition for integral in a generalized sense. So they actually mean to say here convergent. Because again, this is also from an older exam and they had a slightly different definition for that. So with something like this, you obviously don't want to waste time integrating every single one of these. Also because some of them you actually can't realistically integrate, at least not easily. So you want to try to do this as by doing process of elimination. Of course, you do have none of the preceding, so we might have to actually do some work once we're left with like one answer choice. But my point is that a lot of them you can eliminate pretty easily. So anytime you're trying to integrate, whether it's on an unbounded interval or not, the number one condition that a function needs to satisfy is that the function must be bounded. So what I would notice is that the first two are somewhat similar. They're both variations of 1 over a root. This one is kind of a typical situation that we can just save for later. We can talk about it after. But the main thing I would notice is that you have powers in the bottom. So these are all somewhat similar. This one is just an exponential. And it's an exponential with a base bigger than 1. So graphically, it's going to be something like this. And if you're trying to integrate it from 1 to infinity, so you're considering this portion, you can already see that it's clearly unbounded. So we can't even consider integrating it because it's unbounded. So it's definitely not integrable in a generalized sense. And it's not convergent. Just to clarify, notice how if you had taken the opposite direction, it would be bounded. So then maybe the integral could converge. But on the interval that we're considering, it's unbounded. So we're not going to bother trying to integrate it. And with E, this one is a bit different than the classic situation, because in most situations, you again, you have 1 over some sort of a power. Here, it's 1 over E, and then you kind of have almost a negative, not exactly negative power, but almost. And this is also going to be simple enough that you can just graph it, because you can rewrite this as e to the 1 over e to the x squared. Then rewrite this as e to the x squared over e. And e is just a number like 3, basically. So even if you can't graph this perfectly, intuitively, as x gets very big, this is going to get infinitely big. So it's going to be something along the lines of some sort of a parabola. Again, it doesn't really matter what it is exactly. What matters is that as x goes to infinity, you could actually just take a limit. The limit of that is going to be infinity, which implies then that it's going to be unbounded again. So my point is that you can easily eliminate D and E, and so you don't want to waste any time doing the integration for those. Now for A, 1 second, I'm just gonna make some space. So for A and B, you want to recognize that they're both essentially 1 over power. So for A and B, it should be related to the harmonic rule. This one comes up all the time in these multiple choice. And this one says that if you're integrating 1 over a power, a positive power specifically, from 1 to infinity, it's going to diverge to plus infinity when the power is less or equal to 1. And it's going to converge if the power is more than 1. And you can easily see here that if you were to consider the limit of this function, 1 over square root of x plus 2, the plus 2 wouldn't change the behavior, which means this is asymptotic to 1 over square root of x. So essentially the numbers are irrelevant. And if you use the asymptotic comparison test, which essentially says that instead of integrating or considering the original one, you can just look at kind of the simpler one that is asymptotic to, then you can see that this is just a special case of the rule that we just saw, where specifically the power is 1 over 2. And then if you're in the case of the power of 1 over 2, then it's going to diverge. So a lot of times you're just using the asymptotic test, which basically says you can remove the parts that are negligible, which are usually numbers. And most of the time it just becomes 1 over a power. And then you don't even need to do any integration if you know the rule. So it's really just a matter of checking if the power in the denominator is less or equal to 1 or more than 1. And B is super similar. It's just a cube root rather than a square root. But again, when you take the limit, you can see that if x goes to infinity, then you're going to have 1 plus infinity. So we're just going to keep the cube root part, which goes to infinity. Now the power is 1/3, but it's the same situation. And so again, it's going to diverge to plus infinity. And I saved this one for last because it's a bit messier to work with. But then again, when you see that you have a cosine or a sine by itself in the numerator, if it's by itself, it's going to mean that the function constantly changes sign. And when that happens, when the function is not eventually positive or eventually negative, then technically you can't use the asymptotic comparison test, because just like the comparison test, you need to have eventually positive functions. And the only times that you don't is really with sine and cosine. Eventually negative is actually fine as well, because you could just take the negative to the front essentially, and it wouldn't change the situation. But sine and cosine are the cases where we have to use the test that we talked about before. And since this test is only applicable to convergence, then you can pretty much kind of predict that because we don't have a rule for divergence, then most likely we're going to be in the case where the integral of this converges. So this is because when we use the absolute convergence test, if we were to find that with the absolute value diverges, we actually can't make a conclusion. And then you wouldn't have an answer. So in order for them to be able to ask this question, they really have to make it so that it converges. So you could initially basically remove the 1 plus, similarly to the other ones. And then that becomes cosine over x to the 3/2. But then technically you can't use the asymptotic comparison test first. You can't use it yet, I meant to say, because a function is not eventually positive or eventually negative. So we put an absolute value there. And then if we find that the integral of this converges, then we can guarantee that without the absolute value, it converges too. So it's kind of like 1 over power in the sense that cosine is basically just a number between 0 and 1. We can't say that it's asymptotic to 1 over x to the 3/2, but informally it almost is. So intuitively, I would say that if the power here is more than 1, realistically, it is going to converge. But if you have to do it properly in case it's an open answer, you could try comparing to 1 over x to the 3/2. I'm picking that one just because this way, if I keep the denominators the same, it'll make it easy to compare them. And also, this is a case that converges. So if we know that this is between 0 and 1 in absolute value, then this is smaller or equal. And since this is bigger, and we know that the integral of the bigger one converges, then we can guarantee that also the smaller one converges as we expected. So that's the comparison theorem, or comparison test is the same thing, also called comparison criteria. And then because with the absolute value converges, according to the absolute convergence test, we can say that also without the absolute value, it converges too. So technically we have to use every test because actually we use the absolute convergence test, then the comparison test, and then the even the asymptotic one, because we removed the 1. So just if it's open answer, I would at least mention which tests you're using, just so it's clear. But of course, if it's multiple choice, honestly, you can kind of assume that if you have a sine or cosine by itself, it really does end up having to converge because you're forced to use the absolute convergence test. So that's kind of a good thing to keep in mind. Just so that you can kind of guess on it if necessary, but it is, a very educated guess. And also with these ones, even without writing it out, intuitively you can just kind of think of it as the numbers are irrelevant. And you just have 1 over a power. So when you have 1 over a power, it's just a matter of using the harmonic rule. And you can easily see that both of those cases are going to be in a divergent case. So those are clearly not the right ones. So my point is, if you have cosine or sine by itself, it's always going to be really the numerator. Realistically, it's going to have to converge. If it's not by itself, then you might not need the absolute convergence test. Like if you had like a cosine of x plus 2. So then maybe that's not the case. But if it is by itself, you really have to use it. So there's really no other options. Okay, I guess it was just one last one, and this is quick, so might as well do that too. And this is also with absolute value, but it's not really related because it's not an improper integral. It's just a definite integral. You don't need to graph this, but just to understand in general what it means to take an absolute value or the integral of the absolute value. If you have it, for example, the absolute value of, let's say, x, let's just do. The idea is that if we just graph x first, and we want to integrate it also on -6 to 6. When you take the absolute value of something, you're reflecting anything that is negative up to make it positive, which means that anything that you had here, which would give you a negative definite integral by itself, is going to then just become positive. So if, for example, this had an area of, let's say, -1, when you then take the absolute value, it will, when you flip it up, it's then going to become +1. So my point is that we don't necessarily need to know the graph, but we do need to know where the function crosses the x-axis, because that's going to affect where the function is reflected when you take the absolute value. So this would become like this, basically. And whatever this was, it would simply become positive. So the best way to approach this, even if you don't know the graph, is first set this function equal to 0, because that's the point where the absolute value starts or stops reflecting. If you multiply the denominator over, you just get that x equals 0. You could also get more than 1 point in other cases. And so for integrating from -6 to -6, instead of having the absolute value inside, which is messy to work with when you're integrating, you can instead think about it graphically in a sense that if you split it up from -6 to 0, because 0 is our point of change, and then from 0 to 6, we just have to basically take the integral of those parts individually, and then after we do the integral, we make it positive. So for example, here, if you had done the area and it was, let's say, I don't know, -4, the definite integral, then here it's going to become +4. So my point is you simply separate the negative from the positive parts, you integrate them separately, and then for each one, you just take the absolute value after you do the integration. And that's just going to make it much easier than any other method. So my point is, generally, you can't just take an absolute value outside. You can only do that if you've figured out where the function changes sign. And by setting it equal to 0, then you found that point. And so then you can look at it as two separate parts. So at this point, it becomes pretty straightforward because the numerator is almost a derivative of the denominator. The derivative would be 2x. So we can just use the multiplication trick. So multiply by 2 and also a half for both of them. And this way, when you have the derivative over the original function, you can use the shortcut where that becomes ln of the denominator. And then you plug in the numbers. And the other one is very similar. It's actually the same, except that we're putting in different numbers. And then we just do the calculation. So we should have 1/2 and then ln of 1 minus ln of 37. And then we put that in absolute value. And then here you get 1/2 ln of 37 minus ln of 1. And ln of 1 is 0. So here you get absolute value of -1/2 ln of 37. ln of 37 is definitely positive. Because if you know how ln looks, when you put in 1, you get 0. And so when you put in 37, it's definitely positive. So to make it positive, we can just remove the negative sign. And the other one is already positive. And then when you simplify, you just get ln of 37. And this is also equivalent to if they ask you to find the area between the function and the x-axis. It's equivalent to just putting an absolute value like this. So it's the same thing if they asked you find the area between this function and the x-axis. So the key thing is just to find those points of change where the function is equal to 0. Okay. Does anyone have any questions?